So the next task on your group assignment is going to be to establish a proof. So to begin to use some of the definitions of these various sequence properties in the service of writing a proof. So what I'm asking you to do here is to write a proof that if I take any bounded sequence at all, right, so it could be minus 1 to the n, as we were just looking at, or it could be anything. In fact, if it was minus 1 to the n, we would get exactly the two examples that we just finished looking at. So just as a motivating example, if Sn is minus 1 to the n, we just saw that that was a bounded sequence, but that it itself was not convergent. But then we define a second sequence by dividing that first sequence by n. So we would get minus 1 to the n over n in the example where we choose Sn in this way. And so our job would be to show why it is that the boundedness of the former necessarily implies the convergence of the latter. And we just finished convincing ourselves that these two particular examples of sequences, which you provided for us today, but here they are coming back at us in an example, that this was not an accident, right? That any bounded sequence, regardless of whether it converges, if I divide it by n, I get a sequence which does. So if the goal is to do this in generality, and it is, then what we need is to just refer back to our definitions. So again, every one of these proofs is an exercise in recalling definitions and then using definitions. So Sn is bounded. What does that mean? What's the definition of bounded sequence? Okay, so this means that there exists a number m, a real number m, right, such that, how do we want to put this? So one way of thinking about what it means for a sequence to be bounded, right, so I've sort of put sort of a random looking sequence here, but that this sequence is bounded can be captured by saying that there exists some capital M such that what? Every term of the sequence is less than capital M. That would be less than or equal to, maybe. That would be a definition of what we would say bounded from above in that case. When we just use bounded without the above qualifier, it means both bounded above and bounded below. So is there a way of maybe getting to that definition using what we have here?
It's like trapped in between. So it's like negative m is less than or equal to the sequence, which is less than, yeah, that.
This. And for which values of little n should this be true?
Greater than n.
Technically, for a sequence to be bounded, we would want this to be true for all n. Right? Every single term of the sequence needs to be within an m's distance of 0, is one way of saying this, right? Or cannot be bigger than m in absolute value. So another way to rephrase this would be to write that. The absolute value of Sn is less than or equal to m. So let's take that as our definition for bounded, because that captures both bounded above and bounded below. And so this is something that we get to assume. So this thing written in red here, this is true fact as far as our proof is concerned. Right? And what we now need to establish, I'm going to highlight this in a different color, is we need to show that this sequence, the sequence of Sn over n, is convergent. Right? And so let's write that out in its definition. What would be the definition here? For all epsilon greater than 0, for all epsilon greater than 0, there exists capital N such that for all n greater than or equal to capital N, So here I have to have Tn, right? The nth term of my T sequence. The absolute value has to be less than epsilon. But now here we are with this problem. The problem is that our definition of convergence requires us to specify what value the limit has. So one way of doing this would be we could get around this by using the Cauchy criterion instead. Right? So we could instead augment this like that. Right? Say that for all n's and m's that are greater than or equal to capital N, the nth term and the mth term are within epsilon of one another. So that's one way to do it. That would show that Tn is Cauchy. And then we would use the theorem, whose number escapes me, 2.19, no, 2.20, no, 2.40. It's like way forward. 2.40 would imply that Tn is convergent. I think it's 2.40. Somebody fact check me on that? Okay, good. Right, so that's one way to do it. From the perspective of the authors of our textbook, from where I got this problem, that would be a little bit cheating. Be putting the cart before the horse a little bit, because this problem came from the section of the book 2.6. This is a section where we're working on just boundedness properties, so we haven't seen the Cauchy criterion at that point in the book. That means that there's probably a way of doing this without making reference to Cauchy, but as far as I'm concerned, we could do this. And so you might decide in your team that that's what you want to do. If we're going to do this without the Cauchy criterion, then we do have to specify what the limit is. What was the limit in our example? When we started with minus 1 to the n as our bounded sequence, and then we looked at minus 1 to the n over n, what was the limit to which that latter sequence converged? 0. So what we might do is we might make the conjecture here that not only is Tn convergent, but Tn is necessarily convergent to 0. So that would actually give us a little bit more than what the theorem is asking for, which is fine. That's always a good thing, right? If we can prove the sequence converges to 0, then in particular, that sequence is convergent. If we can justify this, then that's what we'll end up doing. And so what you might do then is just reframe this statement down here to remember how we've defined T sub n. T sub n is just S sub n divided by n. Right? And so now this is the inequality that you would somehow have to justify for all n greater than or equal to some capital N. And since all of my little n's are, in fact, positive because they're natural numbers, another thing we could do with this inequality is multiply it on both sides by little n. And that'll give me something that looks like this. Right? And now we're getting down to territory that it feels like we should be able to do something with. Because the statement, the claim we're trying to prove, and the information that we have about Sn, now they look awfully similar to one another. So when you begin to explore how you might write this proof, you might think about trying to prove the latter statement in this form, because the true fact that we get to assume about the original sequence Sn has an inequality in it that looks very like that one.